the video, you will understand if a differential equation is Bernoulli equation, differential equation, or linear differential equation. Now, at this point here, let's compare with the linear equation that we all know. We have it as y prime plus p of x y is equals to x equals to q of x. Now, this is a linear differential equation, but on the Bernoulli differential equation, there is y raised to the power of n, meaning this particular equation is a Bernoulli differential equation. So, since it's a Bernoulli differential equation, we are going to reduce it to a linear differential equation. And how do we reduce that to linear differential equation? So, at this very point here, we know that our p of x is equals to x. That is established, and we also know that our y raised to the power of n is equals to y raised to the power of 2. That is, our n is therefore 2. This is what we have established. But because we know that our n is equals to 2, so we are going to look for a substitution for it. Then the substitution here is we have z is equals to y raised to the power of 1 minus n. And therefore, we're going to have z is equals to y 1 minus 2, which will end up giving us y minus 1. And with this can also be written as z raised to the power of z is equals to 1 over y. And making our y, so the formula is still the same thing as y is equals to 1 over z. So at this moment here, wherever we see our y, here, we can substitute it to 1 over z. But we have a problem whenever we see our y prime. What do we substitute it with? And the idea here is that we are going to differentiate our y. And that means at this point here, where this is not looking like a partial differential equation. So we are going to differentiate our y to respect to x and also differentiate our z respect to x. So this equation is same as y is equals to z raised to the power minus 1. So let's differentiate this. So at this moment here, we have, if we differentiate our y in respect to x, we are going to have y prime. So which is equals to, and when we differentiate this in respect to z in respect to x, minus 1 times 1, we're going to have negative. Then we have z, we reduce 1, so we're going to have minus 2, then z prime. Why? Because we are differentiating in respect to x. Now, at this moment here now, you agree with me that we have y prime is equals to all of this. This man is same as this one. This is a negative, and this minus is same as 1 over. Here we have z squared multiplied by z prime. So here we have y prime is equals to negative z prime over z squared. So at this moment, we have two equations. The first equation is, let's keep this one as one of our equation, and let's keep this one as two of our equation. The second equation. So wherever we see our y, we're going to substitute it as 1 over 1 over z. And wherever we see our y prime, we're going to substitute it with this. So let's go back to our equation. Now, our y prime, we have our y prime to be negative z prime over z squared plus, then we have our x here. Then our y, what is our y? Our y is 1 multiplied by 1 over z, which is equal to, then we have our x. Then on this y square, our y, remember our y is same as multiplied by 1 over z square. So in making this, we are going to have negative z prime over z square, then plus x over z, which is equal to x over z square. I want to eliminate this z square. So I will multiply all two by z square. So when I say negative z prime over z square multiplied by z square plus x over z multiplied by z squared is equals to x over z squared multiplied by z squared. So this we are going to take away this, and this we're going to take away it, and this we take one of it. So we're going to have here negative z prime plus x z, because one of it has been taken, and we have which equals to x. Multiply all through by negative, so that we want this z squared to be positive. We have z prime minus x z is equals to minus x. If you compare this equation with our linear equation, we have gotten back our linear equation. So with this, let's continue. Then at this point, we are going to work this, looking it as linear equation. From here now, remember that our p of x is therefore negative x. So our integrating factor is equals to exponential the integral of p of x dx. So therefore we have exponential in the integral of what is our p of x? Negative x dx. So with this here, we're going to have, when we integrate negative x, we're going to have the integral, the exponential of what? Negative x squared over 2. So we use this integrating factor to multiply all through. So when we multiply all through, we're going to have z prime exponential negative x squared over 2 minus x exponential negative x squared over 2, which is equals to z, this very z, which is equals to negative x exponential negative x squared over 2. So all of this is same as d into bracket. You only take away the z prime. They take away the prime. So you have z exponential negative x squared over 2 over the x, which is equals to minus x exponential negative x squared over 2. So now let's integrate the both side. When we integrate the both side, d exponential z x z exponential minus raised to the power of 2 x raised to the power of 2 over 2 dx over the x is equal to the integral of negative x exponential minus x squared over 2 dx. So when we integrate, the integration here will take away the differentiation here. Our dx will take away dx here. So we are going to end up having z exponential negative x squared over 2 is equals to the integral of minus x exponential minus x squared over 2 dx. So now for we to integrate this, we can use substitution method to integrate this. So for we to use substitution method, we can say let our u equals to negative exponential negative x squared over 2. So when we differentiate our u, we're going to end up having the u over the x is equals to 2 times 1, we're going to have negative 2x, then we reduce 1 from here, the over 2, this cancel this, so we end up having negative x. And the x, something the formula here, so we're going to have du is equals to minus x dx. So divide both sides by negative x, negative x. So our dx is therefore du over negative x. Now let's substitute the x into this. So when we substitute x, we end up having z exponential negative x squared over 2 is equals to the integral of minus x exponential. So we're not writing all of it because all of this is same as u, and our dx is same as du over minus x. So minus x, we cancel this. So we end up having exponential x z exponential minus x squared over 2 equals to the integral of exponential u du. And whenever we are differentiating exponential of x, we are still going to have the x. Or now exponential du, we are still going to have exponential u is still the same as u, the exponential u. So here we are going to have z x minus x squared over 2, which is equal to exponential u. So, and what is our u? We have x z exponential minus x squared over 2, which is equal to exponential. And our u is what? Minus. We have our u here, minus x squared over 2. So at this moment here, then plus our constant. At this moment here, we divide all through by negative exponential x squared over 2, negative exponential minus x squared over 2, then exponential x squared minus 2. So we take this to cancel this. We have z is equals to this, we take away this, which we have 1 plus. And I told you that whenever we have minus here and we are dividing, it becomes positive. So we are going to have c exponential x squared over 2. So this can be written this way, or we can also be written as exponent z is equal to c exponential x squared over 2 plus 1. It's still the same thing. And now remember that we say that we say that our y is equals to 1 over z. So with this, we can end up having our y is equals to 1 all over, what is our z? Our z is 1 plus c exponential x squared over 2. Now guys, this is our final answer. Please try to solve the b part, which says that y prime plus y is equals to sine x, and drop the answer on the comment section. In our next class, we are going to solve a differential equation to determine whether the differential equation is exact. And I have a simple concept in order for we to check if the differential equation is exact. See you.
Shine, code is science, now we define science. For the science, come and fly high. Mr. Dennis, you know the shot.